Good day, everyone. My name is Michael Nokia,
And I'm Mohammed Sheikhi.
and together we're going to be presenting our final year Information Engineering Laboratory project.
Our project is titled Quantum Error Mitigation using Unitary Circuit Folding and Extrapolation to the Zero Noise Limit. Our project is based around quantum computing. Using quantum bits or qubits that are able to store much more information than a classical bit, quantum computing allows for solving computational problems of much higher complexity and size than is practical for a classical computer.
Existing quantum computers are extremely sensitive to noise. While fault-tolerant quantum computers are still decades away, various quantum error mitigation techniques have been developed to help mitigate the effects of noise on the system.
The objective of our project is to mitigate the effects of noise and minimize error using a two-stage technique, unitary circuit folding and zero-noise extrapolation.
To do circuit folding, we first need a circuit. A quantum circuit is simply a composition of qubits and gates. The gates act as operators that affect the state or phase of a qubit. On an ideal quantum computer, this circuit will not have any error. However, on a real quantum computer, there is some noise present resulting in error. This noise behavior can be small, but still impacts the final result. We use circuit folding to scale up the error so that it can be properly characterized. If we abstract the circuit to a black box Q as shown, the circuit folding technique can be implemented as follows. We take the original circuit Q and fold it by combining it with its own identity. This extends the depth of our circuit while maintaining equivalence to Q on an ideal quantum system. However, in reality, the noise level present in Q is scaled upwards by the folding. This results in a scaled error in the folded circuit. Executing multiple folded circuits enables the noise behavior to be characterized fairly accurately. This involves fitting the noise scaling results to a best fit polynomial, which can then be used to extrapolate the result to the zero noise limit. This provides significantly reduced error over the standard unmitigated error.
The above-described QEM technique was tested using a standardized quantum benchmarking method known as randomized benchmarking for single and two-qubit circuits. The downward trend of the plot shows an increase in error at high noise levels. Furthermore, a clear reduction in error with the use of zero-noise extrapolation is shown in the table. This translates to a two-thirds reduction in error. In addition to randomized benchmarking, real-world feasibility was demonstrated on two widely used quantum algorithms, namely QA-OA and the VQE algorithm.
QAOA is used to solve combinatorial optimization problems that are considered NP-hard using classical computation, such as the max-cut problem.
The VQE algorithm was used to simulate the ground state energy of the molecule lithium hydride at different atomic distances. The table shows a reduction in error. The technique does not yet meet the chemical accuracy required to make realistic chemical predictions, but does mostly serve as an improvement over an unmitigated implementation.
Results so far show that zero-noise extrapolation with unitary circuit folding can have positive error mitigation effects on quantum benchmarks and quantum algorithms. That concludes our presentation. Thank you for watching our video and learning about our project. We hope you enjoyed it.
Thank you.